very brief overview of STAMP. So STAMP stands for Systems Theoretic Accident Model and Processes, and it's an acronym that refers to an underlying accident causality model and then some analysis processes based upon that model. So there are currently 4 analysis processes. There is an early concept analysis called STECA, Systems Theoretic Early Concept Analysis. There is a hazard analysis method that's typically used in design called STPA, and that's what the guys and girls next door will be looking at, and that stands for Systems Theoretic Process Analysis. We will contrast that with CAST in a little while. Then of course there is CAST, the accident analysis or incident analysis, and then there is what's called STPA SEC. Now that's cybersecurity, security-focused analysis based on STPA. It's not different to STPA, it just uses a different language and vocabulary, but it's ultimately the same process, but instead of applied to safety, it's applied to cybersecurity. So to contrast the traditional view of safety with the STAMP view of safety, so in the world of Swiss cheese, dominoes and bow ties, accidents are considered to be chains of directly related events, and it defines safety as a management of failures problem. So you manage safety and prevent accidents by preventing failures. That's the prime objective. When you do the traditional analysis, it's all about identifying failures and then how you can manage them or prevent them. Now in the STAMP view, this sort of goes beyond that. STAMP includes the consideration of failures, but it goes much more broadly than that. So it introduces the concepts of control loops and structures as opposed to Swiss cheese, dominoes and bow ties, and it defines accidents as involving complex dynamic processes. So it defines safety as a dynamic control problem. So it's all about thinking about control and structures. And to prevent accidents using STAMP, you essentially think about you enforce constraints on system behaviour, interactions amongst system components using a control structure. So just to talk a little bit more about the accident causality model. So as I said, it's different to the bow tie and the Swiss cheese model because it's based upon systems theory and control theory. So it introduces the concepts of systems, components and interactions, structure, hierarchy, emergent properties, and most importantly, control and feedback loops. And that's the main focus of the STAMP-based assessment processes. Now it's important to point out that it has the same basis as the systems engineering discipline, whereas a lot of the other traditional methods are very much about reliability engineering, which is a different mindset, a different causality model. And the important thing about STAMP as well is that it covers no failure or system behaved as designed accidents. So if you're dealing with an accident that involves potentially software, strictly speaking, software doesn't fail, and so how you address that with traditional methods is difficult at best. And it also addresses so-called systems of systems and services. So in the case of air traffic control, if you are an air traffic control service provider, you provide a service to airlines and airports, and how you would do a safety assessment of that. STAMP is perfect for that type of application. STAMP is based on systems theory and control theory, and this is one of the main models used as part of control theory. So this is just a simple abstract control loop. So at the bottom we've got what's called a control process, and that could be a physical process or it could be an organisation, it could be any number of things. And that process is notionally under the control of this thing called a controller. And that controller influences that process through some form of control actions, which might be direct or indirect, and it receives some feedback from that process, and that feedback updates the controller's process model so that it has an understanding of what the control process is doing, and then it uses that model to influence the control actions that it provides. And those control actions and the mode that they come about is defined by what's called the control algorithm. And essentially what that does is that defines the behaviour of that controller so that in principle the controller can safely control that control process within limits. Now obviously I'm using very sort of engineering technical language, but that's because this has come from control theory and systems theory. So when I was talking about the concept of control structures or hierarchical control structures, it's a bit of a mouthful that. Essentially what we're talking about is these control loops arranged in a hierarchy. And that hierarchy, you start with the physical process at the bottom, and the controller that's in control of that process is directly in control. And as you move up the hierarchy of various consecutive control loops, they become indirect controllers. And the time between a control action happening somewhere up here can take some time for it to propagate down through the control structure. So this is just a generic control structure, just to show you the sort of parts of a control structure you should think about dependent upon your particular accident. So the red box around there essentially highlights the typical technical system of interest, which in an aircraft accident is the aircraft itself. So how did the aircraft fail? What broke? What was, was there an issue with the engines or the radar system or whatever it is? Then above the aircraft we've got some aircrew, so we can start thinking about human factors and cockpit resource management depending on the aircraft itself. Then we've got the air traffic controller, so how were they involved in this? Now obviously this is a simplified model, but you could start to ask questions, well, what happened between the aircrew and the air traffic controller? Was it just radio communications? What about data link communications? What about radar? What about other sensory and sensors and actuators? And that would be the typical system of interest that an aircraft accident might look at. But then there's also the airline operator, and that might involve the maintenance of the aircraft, or it might involve the training of the aircrew. You've got the airport or ATC management. And then when you start to think more broadly using systems thinking, so taking a step back and looking at the bigger picture, what other control structures are involved? So we can start to think about the design control structure, the operations, the maintenance, and even the emergency response control structure, depending on the focus of your analysis. Because you may, as part of your accident investigation, you may be required to look at the performance of the emergency response and how that could be improved or optimized. And then at the very top, you've got the regulatory control structure, the legal, and the governmental control structure. So I'm hoping you can see from this, previously we focused very much on the technology. We might look at the humans and the human factors. We might start to look at the organisational aspects. But when you take a real far step back, you can start looking at all manner of different things. And some may recall from the Tenerife disaster in the top right-hand corner, there was some new crew duty time regulations that were introduced by the Dutch government at the time. And those regulations basically threatened that if you went beyond your allocated time, then you basically get fired and thrown out the door. So there was significant potential pressure there on the aircrew of this KLM aircraft to take off when they needed to. Now you can't say that's a direct cause, but you can say that it's an influence that should be considered as part of the overall analysis.